Right. This is a talk, as it says, and I use the term lightly, that it's a simple guide to what is basically, or what everybody thinks is complicated mathematics, and trying to turn it into simple sums, believe it or not. So we'll see how it goes. I'm trying desperately not to get involved in any of the complicated mathematics, so don't worry about that. People often ask me what I do for a job, and that becomes very difficult because I tell them I'm an RF systems engineer, and then so they even scratch their head on that one. Basically speaking, what that means is that I'm the guy that comes along and links up whole loads of black boxes to an antenna, and then you've got a thing called signals in space. That is, it's got to go from one set of black boxes, goes through space, and ends up at another set of black boxes. And I'm the guy that tries to do all the the mathematical calculations to make sure that if you put a signal in at this end, you actually get something coming out at that end. HF is funny. Most of my stuff I do at microwaves, which gets really even more funnier, but we'll come on to that later on. Right, what are decibels? Deci means 10. Bells means a ringing in the head giving you a headache. I thought I would start at that just so that it sort of lightens the mood. So you, right. Okay, an RF system, as I've just mentioned, consists of things like this. You've got a microphone, you've got a frequency generator of some sort, you've got a coax cable, you've got amplifier, another coax cable, an ATU, feeders, coax cable, and eventually an antenna. And believe me, that is simple. Right, so here you start off with microvolts, and then this thing produces milliwatts, and then this produces watts, and then this has got dBs loss, and that's got loss, and that's got gain, maybe. So you've got a whole range of things here, microvolts, milliwatts, watts, dBs, and everything, and you can't just add them up willy-nilly and get a result out of here, because you've got apples and oranges. If you like, here's your apples, that's oranges, that's pineapples, and they've got kumquats. And so it goes on. And you can't add all of those together and end up over here with grapefruit. So somehow or other, we've got to come up with some method by which we can calculate all of these different things and get the result that we want, so we actually know what's coming out of here, having spoken into this microphone here, or whatever it may be, to get something out at that end that we fully understand. So that's what the job's all about. Let's get started. Right, we got lots of different units. The thing is, how do we convert a lot of those units into something that is common? And the answer is we turn them into dBs. And we can do this with a simple, this is the first and last piece of mathematics. Here's our equation. Right, power in dBs in watts is the log to the base of 10 of power in watts. But you can do it in milliwatts, same thing, and you get the power in milliwatts. So this is the method. It's 10 log power in watt. That's where we do all our conversion. I have to say, there should be a 10 in front of that, and I've made a mistake there and I didn't notice it. We've got a 10 times. So, that's complex maths. So let's get away from complex maths. Firstly, the log bit. which has nothing to do with trees, as I said there. It's a mathematical function. So if we take, and this is the simple bit, if you take the log of 10 of 1, it's 0. Now, once you understand that bit, the rest basically is fairly simple. So, simplistically, any value of 10s is a number of zeros. So, log of 10 has got 1 0, so the log is 1. Log of 100 has got 2 zeros, so it's 2. And the log of 1,000, 3 zeros, so it's 3. And then you've got all the numbers in between. And that's where it starts to get funny. Unless you've got a big calculator and you want to do loads of different things, we end up with, oh, well, what am I going to do here? What am I do with if I've only got 5, if I've got 15, if I've got 17? So we could come up with something that helps us with that. Right. Now, the most simplest thing is we have to understand we start off with 1 watt, which we now know has a dB value of 0. Got that? Are we all clear on that? Got that? Got that in our head. That's good. Let's double the number of watts to 2. And when we double it, the power level increases by 3. If we double it again, so we go from 2 to 4, we go up another 3. And if we go from 4 to 8, we go up another 3. Now, once you understand that sort of progression, 0, 3, 6, 9, and so on, we're going up 1 watt, 2 watt, 4 watt, 8 watts, and so on. So, we know that 1 watt is 0, 2 watts is 3. Got that? Simples. Hopefully it is. So 4 watts is 6, 8 watts is 9, 10 watts, believe it or not, we already know from our bit before, is 1, is 10, sorry. So 2, 4, 6, 8, 10 dBs. And we know that 100 watts is 20 because it's 2 times 10. So if we're lucky, we can construct a simple table of watts against dBs. And this is where we can now start to see where we're going. So here we go. Forward, 1 watt is 0. 2 watts is 3. 4 watts is 6. 8 watts is 9. 10 watts we know is 10. 20 watts is 3 dBs up from that, so it's 13. 40 watts is double that, so it's got to be 16. 80 watts, right, is double that, so it's got to be 19. Add 3 on. 100, again, we know is the 2, so this is 20. 200, 23, because that's double that. 400 is 26. 800, 29, and eventually we get up to 1,000, and that's 30. And you can work it all backwards if you want, like that. So there's the dBs, and there's all the funny numbers that you get backing up that way. So we can construct, if we want, a whole table of watts against dBs in terms of dBWs. So if you like, 1 dB is about 1.3 watts. So we've put that in there just to show where 1 comes in. And 4 is about 2.6, 7 is about 5.1. Now you can see where it is, where we've got all of these numbers in watts, which are all very funny, but over here we've got simplistic numbers. And the answer here is that, of course, we can add all of these things up when they're in dBs, which you can't do when you're in watts. That's the big problem. You can't add things generally in just watts, because how can you add a wattage from a transmitter at 100 watts into a cable that's in dBs? You can't do it. It don't work. You've got to transfer into dBs and then add the two lots of dBs together. Right. So, in practice, what does this mean? Let's assume a frequency generator. We won't worry too much about the microphone. We're going to create it through a frequency generator. Has an output of 25 watts. Right? And from our calculations that we did before, 25 watts is equal to 14 dBW. Now, the coax cable here, let's say that has a negligible loss, because on your bench it's about this long. And it's sort of like less than 0.1 of a dB of loss. So we'll scrap that one. We don't need to worry about it. Then we're going to put it into an amplifier. Now, the amplifier has a gain here of 10 dBs. So now, the output at the amplifier is 14 plus 10, 24. Okay. Then we're going to put it into a piece of cable. Now, we'll assume, just for the sake of argument in terms of this thing, that the ATU itself has a loss of 1 dB, and the cable to the ATU has a loss of 0.5. So, we also know that we're going to put it into a dipole, and that, shall we say, has a gain of 2.2 dBi, 2.2 dBd here. So if we then add that up, our total output is 24 from the amplifier, minus 1 from the ATU, minus 0.5 from the coax cable losses, plus the gain of the antenna, which we're saying is 2.2. So the total output now, because we can add all of these up and take them all away, because they're all in dBs, has an output of 24.7. If we work 24.7 back into your wattage, that's 300 watts. So we started off thinking that we put this amount here in, and we're getting 300 watts out. Now, right, so if we assume our transmitter puts out 100 watts, 20 dBW, and again, we have an antenna type 1 lambda away, because when you're trying to work out all of this business with the when they try and work out all of this radiation hazard business that we've had with from Ofcom and the like, you take 2 antennas, 1 lambda away, and you have immediately lost 18. Ever so funny that last week when I left here and I drove up past the school, there was the whole load of people arguing over the fact that they've got a 5G mast out there now, haven't they? And they're all going on about the fact that you're being radiated. The antenna isn't legal? Of course it is. I know, I agree that it might not be signed, but the antenna is a legal antenna. Yeah, who were you talking to? Oh, I'm sorry, no, that don't work. I'm sorry, the protesters are all RF engineers, are they?
Well, no, but they've done some investigation and
Ah, the paper...
that mean the antenna is illegal.
No,
Illegally, it transmits all right.
yes, that's what I'm saying. The antenna transmits. The fact that somebody hasn't signed a piece of paper doesn't mean to say that it's changed anything. So there you are. I mean, do they actually know what power is being radiated from the antenna?
Well, I've consulted one or two professional people, and apparently
It's what?
they're not 100% sure that it's legal because it's not signed. Nothing's done.
By whom? Ofcom?
But I don't know.
No, Ofcom are the ones who sign it off.
I don't know.
Ofcom are the ones who sign it off that says you've put so much wattage into this antenna, the antenna has gain, the gain comes out, and it radiates everybody.
I think what they're worried about is because it's so near where kids are playing and stuff and radiation. Right beside their school.
Wait, stop. Wait,
No, I'm not.
I'm sorry.
Bubble things up.
And that's the bit they don't understand. The reason being is because the transmit power out of those antennas is not specifically high. The other thing that they don't understand is the radiation pattern.
Sure.
Now, the radiation pattern from most of those antennas are based upon what is called an inverse cosec squared. Now, how many people here understand and know exactly what an inverse cosec squared radiation pattern means? Scratches of the head. Let me quickly explain. Oh, somebody does. Oh, good. Right. I can only draw this. If I had a pencil, I'd draw it. Right. The radiation pattern looks like this. Here's the main beam. There's the first side lobe, there's the second side lobe, there's the third side lobe. Main beam comes out here, let's say has a power of 1. The first side lobe of a cosec squared pattern is 6 dBs down. The second side lobe is the next 6 dBs down, and the third side lobe is another 6 dBs down. Why 6 dBs? That is what the cosec squared pattern is all about. Now, I know all of this because back in 1990, I designed one of the first antennas for the mobile phone system for a company known as Microtel. And it's very stringent upon the way in which the antenna pattern had to be. And it works like this. First of all, how many of you know and understand what is called the 1 over d squared law? That's the propagation law. All of your radio transmitters basically work on that principle, 1 over d squared. That is to say that if you start here with a power of 0 and you go 1 lambda, it goes down by 6 dBs. If you double that distance, it goes down by another 6. If you double that distance, so I've got 1, 1, 2, 1, 2, 3, 4, it's gone down by another 6. Now, to give you an idea of what that actually means, there is a satellite out there that was launched in 1974 called Voyager 1. It is 38 billion miles away. Unfortunately, they managed to just reconnect to it. It took them 3 months because it takes 1.5 months for the signal to get there and 1.5 months for the signal to get back. It took them 3 months to know it worked. Sorry.
Just to put things clear, when you say 1 lambda,
Yeah.
what do you mean by lambda?
Whatever lambda is.
Yeah, but what
No. Whatever lambda is. If the wavelength, one wavelength, sorry, lambda, one wavelength. I apologize. I thought you understood. One lambda, one wavelength, right? One wavelength, I lose 6. 2 wavelength. So, and remember they're working at nearly 2 gigs. So 1 wavelength is roughly about this. So that's 6 dBs down. That's 12 dBs down. That's 18 dBs down, and so on. And we haven't even got to the bottom of the mast. I'm already 20 dBs down from the bottom of the mast. So if that's transmitted, let's say 10 watts, right? Let's call it 20 dBs down, right? 10 watts, that was what, 10 dB, right? I'm now at minus 10 dBs, 10 dB and 10 dB, right? I'm in milliwatts now. Already, I'm in milliwatts. Big problem is this. You're in milliwatts. Hold on a minute, I'm just going to take a phone call. Oh, that's 3 watts going straight into the head. 3 watts. Not milliwatts, 3 watts. Got it? That's 3 watts that I'm doing there.
But they got that marked right beside the kids.
But it's going to the inverse square. Where the kids are, you're already minus 12 dBs down on the beam.
But what they've done there is they put it right beside the school playing field.
That is where it, yes, fine.
Right.
But they're wrong on the amount of power that is actually being radiated into
maybe, but that's where there is.
and that's what they're not looking at.
And
Anyway.
Another one just over in the car park.
Yeah.
Over there, the side of the road.
Just stop all
I'm not advocating whether it's right or wrong. I'm just telling you that when you do the sums, the so-called professionals that they've brought in, a professional will tell you that the amount of radiation that they're getting is minimal compared to that thing that they put right in their ear hole. Even if you held that there, this radiates 3 watts at its maximum power. And you are literally 1 lambda away. So 3 watts, right, coming out of this, 1 lambda away, you lose 6 dBs. Even if that was broadcast in 100 watts, you still wouldn't have the power going into you that has there when you're using it. Yeah, you can't because they are not RF people that understand what this is about. Anyway.
Where were we?
Where were we? However, that's the life. That's the life of an RF systems engineer, because that's the sort of thing that we actually have to do, is to try and basically tell people what is reality and what is what they think. I had the same problem when I was putting up an antenna, a 6-meter dish out in the Middle East, and which has a gain of 54 and everything and speaks to satellites up there. When we put it in, it was the 3rd one that we'd put in, and when we switched it all on, it didn't lock the modems up. It's what it should do. Switch it on and the modems will lock up to get the signal. Modems wouldn't lock. Didn't understand. Switched everything off slowly. Looked at the output. If anybody understands a QAM diagram, how many people, Don will understand what a QAM diagram. This was the QPSK diagram. 4 fuzzy blobs on the screen.
We touched on it a couple of weeks ago.
Yeah, covered. 4 fuzzy blobs on the screen. Switched everything off. All we had on was the antenna and the scope that we were looking at on. And there were still 4 fuzzy blobs on the screen. And we thought, hold on a minute, this is coming from somewhere else. It's not coming from our kit. And it's not coming from the satellite because it's... We went outside and mile and a half away, there's a tower with a microwave dish. Well, there were 3 microwave dishes. We inquired about what the microwave dishes did. Was one of them on 11 gigs, which is where we were? Yes, they said. We've got one somewhere in the region of 11 gigs. Oh. Scratch his head. A few minutes later, my mate, who's in the monitoring station, says, it's all working, everything's brilliant, no problem at all. Nice little Filipino chap comes in, knocks on the door and says, is your system working now? Yes, we said, it's great. 2 minutes later, he went back to where he works, and the whole thing went to rats. Nothing again. And I thought, one of those microwave systems over there is jamming our satellite terminal. And they said, hold on a minute, that's 1.5 miles away, and it's pointing over there. And your antenna is pointing over there. And I said, So I said, right, how much power does that put out? Only 1 watt. Good. That puts out 1 watt. 0 dB. Got that? 0 dB. The side lobe on the dish is at -40. So we're looking at something now, started at 0 and is -40. What we call the free space path loss. That is the loss between that thing over there and me over here. Was 110 dBs, which is basically nothing. So it's now hitting us at -40, -110, which is -150. All that? So we've now got a signal coming into us at -150. The side lobes on our dish are roughly -30. So it's now receiving into our system -40, -110, -30, -170 dBs. Right, tiny. The signal from the satellite is -210, which means they were jamming us to the tune of -170 to 110. Basically 40 dBs of jamming on top of us. And I had to write a paper basically explaining that although their antenna was pointing over there and our antenna was pointing over there was enough energy getting into our system to basically blot us out to the tune of 40 dBs. Right? So that's why we do the type of calculations that we do. And that's why, as I say, once you understand how you add up and take away things in dBs, it's just sums. Add this, take that, and so on and so forth. Whereas if you try and do all of these things in, that was broadcasting in watts, and ours is receiving in dBm, you've got to make everything all in the same way. Okay, so that's gone off the subject a bit, but there we go. So we lose, every time we move a lambda, we lose 6 dBs. The other thing to remember is that if you've got a horizontal dipole and you want to talk to somebody with a vertical monopole, you're going to lose 18 dBs because of the 2 polarizations. So although you say, well, I'm putting out 100 watts, you're only 2 or 3 miles away, and I can barely hear you. Why is that? Well, I've got a such and such vertical monopole, trap monopole, and I've got a G5RV dipole. You've already lost 18 dBs on top of the loss between point A and point B. Right. You're lucky because at low frequencies, below a gig, you don't have to worry about things like atmospheric problems and things like that. You start going up the frequency band. Has anybody ever seen the plot of attenuation against frequency? I know Don has. It sort of goes up like that, and there's a big peak at 60 gigs, and then it drops back a bit, and then it goes up here like this. And then there's things called weather, like rain. How many of you have got a television that runs on Sky satellite system or the Astra satellite system, whether it's FreeSat and everything? And when there's pissing it down with rain, the whole thing just disappears. Why is that? It's because the attenuation of the rain overcomes the signal-to-noise ratio you need to make your system work. And that's sort of like something like about 5 or 6 dBs, just disappears on you as soon as you get a heavy bit of rain. And the thing that you, and sometimes you think, well, that's strange because it's bright blue sky out there, sun is shining. However, back in London, where they have got their big dishes sending it up to the satellite, it's absolutely chucking it down 30 shades of shit. And of course, they've lost the signal on the up path, not to you on the down path. So you've got double jeopardy on both things. Right. Okay. Where are we? 100 watts. We've got a transmitter. It transmits 100 watts. Right. Right, we put it into 2 antennas, 1 lambda apart, and we immediately lose 18 dBs, just having 2, just from this point here to this point here. You've already lost 18 straight away. Doesn't matter what you do. And then you move the other transmitter away and away and away to the... Going back to what I was saying about the Voyager thing, it's 38 billion miles away, and the signal is so high. Signal to noise is like that. How far has the satellite got to travel for it to lose 6 dBs? The answer is another 38 billion miles. So it's been up there for 50 years, and just to lose 6 dBs, it's going to take another 50 years. It isn't a case of, well, it's only got a few more 100 miles to go, and suddenly the signal will collapse and disappear. You only lose 6 every time you double the distance. Right? So it's 38 billion miles away. And you've got to go another 38 billion miles away for that signal to drop by another 6. So they're going to keep listening to it. The thing is, of course, obviously with that, at the moment, the batteries are basically, it's the nuclear batteries that they're using are running out. It's nothing to do with anything else. The nuclear batteries are now running out. So you won't be able to find out that it's still there in another 50-something years' time, because the batteries will have died and it will just be going through space like a lump of metal. Right. Where are we? Let's say, right, so if we do something like this, 50 kilometers, we've lost 104 dBs. Right? This is this free space path loss. What it is that you start off, here's your signal, and you start to broadcast it. And it goes out as a cone, like this. That's how the signal will go out. It will go out like a cone. And that's where the 1 over d squared comes from, because the cone's diameter is based upon the d squared cross-sectional area. Right. So we've gone 50 kilometers. This is something like on 2 meters. Forget HF here. This is things like on 2 meters. You can lose about 104 dBs. So we started off with our 20 dBW, and We then lose 104, so we're down 84. Or that's dWs, so that's equivalent to 54 dBm because the dBms are 30 difference from Ws, if you weren't aware. That's because it's 1,000. Right, so 1 watt is 0, but 1 milliwatt is 1,000th of your zeros, which is 30 in our dB scale. Right. So, 100 kilometers, we've lost about 110, or down to minus 60 dBm, and the sensitivity of a 2 meter is about minus 120. So you can hear those signals. This has got nothing to do with it going over buildings getting in the way, hills getting in the way. This is basically straight three-space path. However, as I say here, that yes, as soon as you put hills in the way or put multipath in the way, then everything goes to rats. But you should be able to actually calculate from what you put out into space with the antennas and everything, with the space path loss in dBs. So do it in dBs, the loss is in dBs, and you can calculate whether or not you can actually receive that signal. So when somebody says, well, I don't understand, I can't hear him, and yet he can hear me. Because if he can't transmit back the same level as you, i.e. the power he's got, the antenna he's got, and so on and so forth, all of your gains and losses, then yes, he can hear you, but you can't hear him, or vice versa. You say, well, I can't hear him. Don't understand why I can't hear him. And the answer is because if you can't work out what that sum is between his power output, the losses in space, to the sensitivity of your antenna gain and your receiver, then you can work out whether or not why it is he can't hear you, or you can't hear him. So that's the way that works. All right, just to give you some idea of what some of this means. Right, we've got a 3-element beam on 14 megs. Now we're going to say that the gain of the 3-element beam is approximately 7 dB-ish. Doesn't really matter, 7's a good number. Right, there should be no need for an ATU. That should be a no rather than an MP. Right, so we are going to have an output of 100 becomes, I've put in here 24, so that's 400 watts. 24 dB, 400 watts. And we're going to have a bit of cable loss. 0.5 of a dB, so we're down to 23.5. And then we're going to have a gain of the antenna at 7. So the total is 30. Right? So we started off 400 watts, put it into an amplifier. Sorry, just put it into our 400 watts, as we used to have in the old days. We were allowed 400 watts, yeah. We're going to put it into a 3-element beam, gain of 7, we got a bit of cable loss, and we end up with an output of 30.5, which if we go back, we just remember that 30 dBW is 1 kilowatt. So we're actually pushing out from the antenna 1 kilowatt. So that's a fairly simple sort of sum. You've got a 400 watt transmitter, you put it into a 3-element beam, you're putting out a kilowatt. Now you think some of these Italians, they already start here at 30, 1 kilowatt, and then they put it into a 5-element beam, gain of about 10. So this 30 suddenly becomes 40. Well, 40 is 10 kilowatts. They're transmitting 10 kilowatts. And you think, well, I don't understand how it is that I can hear him in the Italian, he's fine, and he's 5.9 plus 20, and he gives me a 5 and 2. Because you've put 100 watts into your dipole. He's broadcasting 10 kilowatts. But then, okay, fine. So if we did this with a 5-element beam on 2 meters using 50 watts, right? So we'll call the gain of the antenna 8. That's an approximation for our 5-element beam, 8, anywhere between 8 and 10 if we're lucky, right? Feeder losses are going to be higher because it's at 2 meters, so we're going to take off a dB. But here we go, 50 watts is 17. Just to give you some idea, 100 watts is 20. We remember that, 100 watts is 20. If we take off 3 dBs, that's 17, and 3 dBs is half 100 watts. 100 watts down to 50, 17. And we take another 3 dBs off of that, it's 25. So, you've got your 50 watts is 17, we take away 1 for our cable losses, and we add 8 for our gain of our antenna. Total is 24, which equates at the end of the day to 250 watts EIRP. So your transmitter is putting out 50, but actually you're radiating 250. And that's with a 5-element beam. If you've got a 5/5 stack or something, that'll push that up. Two lots of 5 by 2 elements, one there and one there, phased together. That's going to push your gain up by 3. Right, so your 8 then becomes 11, and this becomes 27. So you're heading towards your kilowatt here, and you only put 50 watts in from your transmitter, but you're radiating 800 or 900 watts. So that gives you some idea of how, when you're doing these sums, what you're up to. What we have to worry about then is this thing, because we all read about S points, don't we? We're paranoid about S points. 5 and 9, 5 and 8, 5 and 5, whatever it is. One S point is, and this is the bit where it's useful to know about the dBs as opposed to the watts, because one S point is 6 dBs. This 6 dB thing comes in everywhere, right? Path losses, everywhere, you name it. That's what 6 dBs does for you. Basically speaking, the S point is based upon the fact that if you double the distance or halve the distance, it changes by 6. So that's why S points are done in 6 dB steps. It's all to do with the path loss equation. Right, so you have 100 watts, 20 dBW from your transmitter. And the power level at the receiver would only drop by 1 S point, right? We're going to drop the power by 1 S point. 20 minus 6. 20 dBW minus 6, 14. So that now equates to 25 watts. So if you had a 100-watt transmitter and it was giving you 5 and 9, if you only used 25 watts, it would go down to 5 and 8. So, if we do it the other way round, right, so you would need to go, if you wanted to get back from your 5 and 8 back to a 5 and 9, right, if that's what you had, you received it as 5 and 8 and you think, oh, I could do with a 5 and 9 signal. So you've got to add 6 dBs, which means that you, instead of having just a 100-watt transmitter output, you've actually now got to have 400 watts out to have given you your 1 dB back. What comes out of this is that propagation losses and antenna patterns have more effect on the S figure than the actual TX power. And when people go on about the amount of power being transmitted by their transmitter, and that coming from all the other effects around you, have much more influence on the signal level. Now, I've given a standard example of the normal 80-meter net that we have either on Monday, Wednesday, or Saturday. And Derek, Les, and all the others were all within 2.5, 3 miles. I picked Les up 5 and 9 plus 20. I picked John up 5 and 9 plus 5. Derek is 5 and 9 plus 5. Sorry, he's 5. And you think, hold on a minute, he's broadcasting same as us, somewhere around about 100 watts. Why is it that John and Les are 5 and 9 plus and Derek's only 5 and 5? And the answer is that my dipole points out that way, straight into Derek as a null. That null can be anything like 40 dBs deep. Well, let's look. Theoretically, I should pick him up at 5 and 9 plus 5 and 9. But he's 5 and 5. So he's 4 S points down. 1 S point is 6 dBs. So he's 24, 25 dBs down, which is basically what you would see in a null, somewhere between 25 and 40 dBs. Whereas Les and John are not in the null. So they're way up there and can give me 5 and 9 plus 5, 5 and 9 plus 10. So when everybody's saying, I don't hear him, I don't understand why it's not working, S, right, in terms of how much you can lose, is where it all comes from. It's got nothing to do with this, which is what everybody seems to worry about, which is why, even if you're a M7 and you've got a 10-watt output, you can still manage to talk to people in exactly the way as a G4 or a G7 or a G something else can do on 150, 200, 300 watts. The difference simply being that, yes, you can receive him 5 and 9 because you've got 400 watts, whereas your M7 is receiving at 5 and 4, 5 and 5. But obviously, if you're receiving the signal, does it matter? And that's the thing. Everybody seems to be wound up in the fact that I've got to have 5 and 9 plus, etc., in order to get the signal. And really, when you start to understand that every time you go down by 1 S point, you're losing 6 dBs. And that really shows you how much little power you end up just by being an S9 down to an S5. And that's, in a way, is why a CW signal from work on such low levels, because you're not worried about the S level that is basically coming into you. As long as you can hear it and you've got it, yeah. Everybody knows, you know, you go, oh, well, yeah, 5 and 9, you're 5 and 9, you're 5, 9, 9, when in fact you're looking at it and it's barely moving the signal. And half the time, how many of us are saying, oh, yeah, you're 5 and 9, but are you 5 and 9? Yes, you're 5 and 9, providing when everything is basically, I'll say, switched off, other than the fact that your receiver is on, S is 0. But it's not. How many of you got S where it's 7, 8, 9. So your S number is not 5 and 9. It should be 9 minus S7 for the noise. So you're only really S2. You're never 5 and 9. The bit that you actually see the needle go to is almost immaterial. What you need to always measure, and as we do, as Don will tell, in the professional field, we measure signal to noise. We do not measure signal. Amateurs only ever measure signal. Professionals, if call it that, professionals measure signal to noise. If you're ever doing anything like digital stuff, depending on the type of modulation that you're using in digital, signal to noise is the most important thing that makes the whole thing work. If you're using some complex QAM modulation, you've got to have a signal to noise of, say, 20. Whereas if you're using some really highfalutin codec code, it may only be 2.5 to the only 2.5 dBs high. TV signal, 23. Some of the flashy signals that nobody talks about, 2.5 if you're lucky. In fact, we get down to as low as 0.75 at times with some of the stuff that goes on. So, when you're talking about S numbers, signal to noise, not just signal. And yes, you can say, oh, you're 5 and 9 with me. No, you're not. You're 5 and 2. Right. Oh, here's the other. You name it.
Your favourite number.
The favourite, everybody's favourite thing. VSWR. God, the number of times you listen to people talking about VSWR. Right. Here we go. These are the VSWR numbers. This is really what you're looking at, is the thing called return loss. Forget these. These are made up things. This is the bit that really gets you measured. Anybody that's got a VNA thing should really be using the thing called return loss. That tells you something. This doesn't. What is important is this thing, the mismatch loss. And look, the amount of loss that you get, you got a 100 watt transmitter, and you put it into an antenna at 6 to 1. Not 1.1 to 1, 6 to 1. You will have only lost 3 dBs. So you're pushing out still 50 watts. You started off with a 100 watt transmitter. Look at that. Pushing it into an antenna of 6 to 1, VSWR 6 to 1. And all you've got, you've lost is half your power, 3. So you're pushing out 50 watts. That's nothing to do, by the way, with the fact that your reflective power, you're putting out 100 watts in and you're putting 50 watts back into the transmitter, which is not doing it a lot of good. Now, I do not advocate that everybody starts broadcasting and transmitting at 6 to 1 into their modern transmitters, because it won't take a 50 watt replay. But in the professional field, 3 to 1 is fairly standard. If you've got an antenna, and if you've ever put antennas, as I have, on aeroplanes, if you can get the VSWR down to better than 3 to 1, you're lucky, because of what you're having to work with. So that's fairly standard in the professional field, certainly in aeroplanes. VSWR of 3 to 1. That's all you usually expect to get. We use other techniques to make sure that the 25 watts that is coming back isn't fed back into the transmitter. We tend to use a thing, if you're not aware of it, it's a thing called a circulator. You put a circulator on the output. This is a 3-port device with the first port at a quarter wavelength and the second port at half a wavelength. And what happens is the power goes out, round to the quarter wavelength and goes out to the antenna. The reflected power comes back, but then goes round to the half wave point, and if this is an open, that's a short, right? And then goes down into a load, a 50 ohm load. And it won't go back round, back into the transmitter port. So that's what is used to make sure that your 25 watts coming back doesn't go back into the transmitter and blow it up. And you think, if you ever did a broadcasting transmitter, you have to think about this very hard. If you've got 500 kilowatts going out onto a medium wave transmitter and the VSWR starts climbing up a bit, and you start off with half a megawatt, and you've got something like about probably 2 or 3 kilowatts coming back in your VSWR. You can't have that going back into your transmitter, so you've got to do something about it. So the answer is you use what's called a circulator, or a device like a circulator that dumps that residual power out of the way and it never gets back into the transmitter. What it means is that, or what we're trying to get at, is that really up till this point here, 2 to 1, right, you're only losing a small amount of, you're only losing barely 10% of your power is going back into the transmitter. And the amount of loss at 2 to 1 is half a dB. You'll get something higher than that on a crappy connector. So when you're striving to get this 1.1 mythical point on your system, what are you going to achieve? Absolutely nothing. Even if you were at 1.3, you can't even see what it's doing. And at 1.5, again, hardly anything to notice. So all of this talk about getting VSWRs down to ridiculously tiny numbers and suddenly your antenna works so much better is a myth. And certainly anybody that has actually knows your receive, if you have a receive antenna into your system, the VSWR can be crap like this. It doesn't really matter because you're obviously not putting power back into any sort of the back of the receiver. But your losses are tiny, almost non-existent. And remember, your receive antenna can have a VSWR of 6 to 1, and you've only lost 3 dBs. Half an S point. Half an S point, because your receive antenna, really, it doesn't have to be this. You won't notice the difference at all. So much. You just listen to people going on about having VSWRs that are absolutely brilliant. And it makes their system so much better. Really, it isn't. It doesn't make any difference, or very little difference, until you are really getting down here. And even in a receive, and they say, oh, well, it's so much better on receive. And you think, you can go down to that on receive and you won't notice the difference. You look at the difference between connecting a piece of long wire onto the back of your receiver, something that's 20 or 30 feet long, and a proper dipole. You barely will notice the difference. Right. What does all this mean? Well, that's where I said it's you know, the decibels, basically, that's the bells bit gives you the headache. Right. So, A VSWR of 1.1 only is going to lose you 0.2 of a dB. And you'll get 0.2 of a dB. There's 0.2 of a dB loss in a connector, one connector. So if you go and add another connector into your system, another piece of cable, whatever it is, you've already created 0.2 of a dB in your system. And that doesn't change. So even a VSWR of 2 only loses you 0.5. And you wouldn't even notice that, half an S point. And so on. And as I say, remember, 1 S point is 6 dB. So even at 6 to 1, you're only losing half an S point. Right. Looking at the time and making sure that I finish before 9 o'clock and that there's time for people to try and ask me questions. What I'm trying to say is if you can understand the way in which dBs work, as opposed to the way in which watts and milliwatts and everything else, and you can convert into dBs, the whole of the RF system that you use becomes more easy to understand and explain. You can't do it just with watts or milliwatts or whatever it is that you do in the other measurements. If you do it in dBs, it will basically work for you in terms of just simple sums, adding up, taking away, add up here, take away there, add up, all the way through the system. And then you can work out whether or not that's then going to make it to the far end. And all I'm trying to say is try and, if you can, read up about it and try and understand, because RF then becomes so much simpler than what you think it is if you try and work and get your head around the idea of, oh, well, it's in watts and I've done this. Antenna gains are in dBs. Amplifier gains are in dBs, everything. And even if you go through your single sideband transmitter, you've got mixers. The mixers have got loss in dBs. The amplifier bits have got gains in dBs. And so on and so forth. Bits have got gains and losses in dBs. You don't work them out in volts and millivolts and all of that sort of thing. So there we go. It's trying to... I thought I would add this on to the end, just to give you an idea. Unfortunately, it's very tiny, but this is my day job. And this basically, this is a satellite, what's called a satellite link budget. So if you like, you start off here, which is ground station, and you've got an output from a modem, and then you put it into a up converter, and then into an amplifier, and then into some waveguide, and then into an antenna, and then the antenna broadcasts it up into space to a satellite, and then it goes through the satellite, and then you've got a satellite translator frequency, and then into another antenna that then beams it down to the Earth, and then it's received by another antenna that goes into some filters, and then it goes into a converter, and then into a low noise amplifier, and then so on and so forth, till eventually ends up in into the modem at the other end, and that you hope that the signal that you put in at one end comes out at the other end. And what you've got in the middle is all of these various bits of calculation, because it takes into account rain fade, atmospheric fade, the size of the antenna, all of those sort of things. But because you convert everything where you can into dBs, although it looks complex, really at the end of the day, it's just adding up and taking away all the way through. So you start off with a known signal at the start, convert it into dBs, run it through all the various bits with the gains and the losses, all through space, all through the satellite, comes back down, and then again through all the black boxes at this end, and eventually you convert that back into a signal that gives you a brackets, an S reading, or the equivalent of an S reading. And then you know whether or not that S reading has got enough signal to noise to make the digits come out properly. So that's what I do, and that gives you some idea of the complex. If you, as I say, it's all very tiny, but that's the complexity of it all. That's the day job. And that's about it. So, questions?
And do part of what you do, you actually prove it as you see it. I go through
The answer to this, the answer is that I have worked up one of these tables, and if you like, my calculation says you put in certain signal level in here, and when it all comes out at the bottom end, we get a certain level signal there. I then, basically speaking, run across to a transmitter ground station, satellite transmitter ground station, and say, could you please put that level of signal in, and then detect it up through the satellite and back again, and tell me what the number is out here.
So you might.
And within something like about 0.2 of a dB, all of that calculation works.
Wow.
So it's basically been ratified by the powers that be, that the numbers that I'm using, because in there you have to make brackets assumptions, and that's the bit. Those are the bits that basically say, well, this is what I think is going to happen, and so I've allowed a number to be put in there. And you hope that number is right. But when you go and do it for a real measurement, and it comes back with an error of about 1 to 2%, then you think, my assumption is correct, so I'm fine, and that's good.
That always good. Yeah, brilliant presentation. It takes you back to my army apprentice days.
Good.
Brilliant.
Yeah, very good.
But my brain would never be able to absorb that now. Where would I find a booklet or whatever to revise me?
You probably, actually,
Go
the
on,
best
away.
thing to probably do is
I can't hear you.
sorry, the best thing is, if you like, is Google, and look up Wikipedia and put in
Big artisan.
simple dB type
Yeah,
things.
I'm with
That
you.
is your, rather than, if you go into books, and I have to say this, to start looking at this, right?
Yeah.
You will get all of the bit that I have really left out. And that is a series of quite complex equations that they'll come and talk about, and this, that, and the other. And for people here, you don't need to know all of that. There is no point in learning about that. If you go onto Google, you'll get a much more simplified approach, something that you as a person can understand, and people in the room should be able to understand, because it's relatively simple. I'm not saying there isn't maths, but it's relatively simple maths. As long as you understand the 10 log 10 bit, that's the most important bit, because even in here, we convert, we do a lot of things. One of the things you have to look at is, if you like, what's called space temperature. Space has a temperature, right? For HF and VHF, nobody worries about it. But when you get up into microwave region, space temperature suddenly becomes important. You've got to convert temperature, or the impact of the temperature that you're looking at, into dBs. And you do it by exactly the same thing, 10 log brackets temperature, turn it into dBs, and then that goes into one of the sums. So everything that you do, you try and convert over into dBs, 10, log, brackets, whatever it is that you're looking at. Now, some of them come in. One of the things which amateurs never know or understand, and yet if you're a microwave engineer, it's one of the first things you learn about. I know Don knows, but how many others here know about the thing as known as G/T? None of you, right? To me, that's one of the, if you design a dish antenna, G/T is one of the most important things you have to know and understand. It basically is gain over temperature. It is what is known as the goodness factor of a dish antenna. So even your Sky dish at the back has got a G/T. It's a square root of crap, but it's got a G/T. Basically, what it is that you have a gain of an antenna. Let's say it's 40. And then you divide it by all of the temperature things. That is space temperature, 273, right? You then also have the temperature of the amplifier. That has a temperature, has a gain, a noise of say 0.6 of a dB, but that basically translates into a temperature. Pieces of waveguide, cable, all have losses, which are temperature. You add all the temperatures up and then convert that into dBs. You've got the gain of the antenna in dBs, and you basically then take, because we only ever do adding up and taking away sums in dBs, that's the advantage of it. You start working in kilowatts and watts and everything, and you have to do multiplications and divisions and everything. You do it in dBs, and it's adding up and taking away. And that's why I say, I just do simple sums. I add it up and I take it away. And I used to say this to people. So look, during the day, I do these adding up sums and taking away sums. And then if I go somewhere, I've got expenses, and I do the same thing. I do the adding up and the taking away of my expenses and put them in at the end of the week. So everything I do is just adding up and taking away. And I don't do anything more complex than that.
One other point, though. Does all this indicate how the reasons for us having difficulties from the Middle East, Far East obviously is distance, but the Middle East sometimes it's an absolute pig to actually go from this wadi to that one.
If you're transmitting HF long distance,
Sorry?
if you're transmitting long distance on HF,
HF?
on NHF, and it's bouncing off the ionosphere, etc., right? There's a whole raft of completely different sets of equations compared to your 2 meters that is going from your house to the house 50 miles up the road. That's straight free space loss.
Yeah.
Right? The bit that you can't quantify, because it's not a, let's say it's not a stable number, is the atmosphere. You've got no idea, which is why you can go on 7 megs this evening and go from here to Australia, absolutely no problem at all. Tomorrow night, you're barely lucky if you get from here to the southern coast of France.
Yeah.
Because that up there doesn't have a constant value. It is forever changing on a day by literally minute basis.
But there was much head scratching over Borneo to Australia, and it worked. Trying to do anything back to England, you were marking time.
Remember that if you're an HF,
Yeah.
you don't know how many times you hop.
Sorry?
You don't know how many times you hop.
Oh,
You do not necessarily go up and down
with you.
like that. Sometimes you do that,
Yes.
and it could be 4 or 5 times that it does the bounce before you get to the end point. Sometimes it just does it in one bounce.
And it's daylight and night time is well different.
And all of that changes literally minute by minute. Now, again, if you, like Don, if you've ever done NVIS, near vertical instance skywave, okay? Where you transmit from and to depends literally on the day of the year, the month, and the time of day. They have, the MOD have tables
Yeah.
that says today is June the 21st. It is 9 o'clock. To get from point A to point B, use, let's say, 8.37 megs.
Yeah.
But tomorrow, you read the same thing and it say you use 9.25 megs.
And also the type of antenna.
And all of those sort of things. But we're assuming we have a standard, what I would call NVIS antenna, one thing that will go and...
The Navy used, the Navy used HF back in the good old days, we used to carry a book and it was done by position on the surface of the earth. So if you had traffic, wherever you were on the earth, if you had traffic to clear by CW back to the UK, you just looked up your ship's, got your ship's position, looked up your position.
On a modern
and
ship's
time of day.
transmitter, which has on a modern ship's transmitter that has NVIS capability, right? They also have what are called scanning, very fast scanning transmitters and receivers. Literally will scan from 2 megs to 30 megs in a matter of less than 1 second. You are on one end, you transmit on a frequency, right? And the receiver at the other end is literally scanning across, trying to find that thing. And then it will find it, and if it finds it, it will then basically try and lock up, and if it can, it will transmit backwards and forwards. If it can't, then the transmitter will shift frequency, right? And then do it again. But the transmitter is also scanning from 2 to 30 megs in a matter of a second. This is doing 2 to 30. And so when the signal works, right, that it gets it, then it locks its all self up. And it's literally done almost instantaneously because modern professional type transmitters and receivers can scan that fast, right?
Yeah.
And transmit and scan at that fast, that sort of rate.
You can see those signals on HF.
What happens to the receiver at the other end?
What do you mean, what happens to
Well,
it?
you're transmitting here and it's going all over the place. What happens to that when if they haven't got the same signal?
No, because it works reciprocally. It doesn't matter. This one can be transmitted on, let's say, 7.5, but it's coming back on 9.2.
Well, that's what I'm saying, you know.
Yeah.
what's
It will work like that. As long as it can make the double link back, it will try and look for the way of doing it.
There's an American signal, Mill Standard 188, which is an AIL system, automatic link establishment. That was an early one. And it's just doing that all the time.
All the time.
Just looking for, as soon as you get a link, locks up, boom, traffic goes. And then it's off again.
There are all of these, as Don knows and I know, you've got all of these standards.
Yeah.
The one that I tend to do a lot of work with is a thing known as, I sort of know it forwards and backwards, 188164, which is all to do with satellite communication, RF stuff. But you've got MIL standards, you've got DEF stands, you've even now got EC, which are basically European community standards run by the likes of Inmarsat and Intelsat, etc., that have got ways in which you have to sort of create these things so that you can build equipment here and here so that these things will work together. And that's, if you like, that's what we do.
We looked at one a couple of weeks ago, it was a Stanag.
Yeah, and there's Stanags as well and all of those sort of things. Right, anyway, thank you very much. I hope you've enjoyed the